Welcome for the session. Today I am discussing some of the numerical on SFD and BMD. Draw SFD and BMD for a beam shown in figure. Simply supported beam is given, which is supported at point A and B. 2 kilonewton and 4 kilonewton load is applied on the beam. We are using conditions of equilibrium to determine the reactions. Summation of Fx is equal to 0. Summation of Fy is equal to 0. Summation of moment about point A is equal to 0. Here we are going for summation of Fy and summation of moment. Summation of Fy is equal to 0. Vertically upward force we are taking as a positive, vertically downward force as negative. So at point A and D, reactions are there. So Ra and Rd are vertically upward, whereas 2 kilonewton and 4 kilonewton are vertically downward. So Ra plus Rd minus 2 minus 4 is equal to 0. So we can write Ra plus Rd is equal to 6 as the equation number 1. Next, summation of moment is equal to 0. Clockwise moment negative and anti-clockwise moment positive. As moment is the product of force into perpendicular distance, whereas 2 kilonewton and 4 kilonewton are clockwise in nature, so that are negative, and force RB, which is anti-clockwise in nature, so that is positive in nature. 2 kilonewton load is 2 meter away from point A, so 2 into 2 is the moment of 2 kilonewton. 4 into 6 is the moment of 4 kilonewton, and RD into 8 is the moment of RD. From here we get RD into 8 is equal to 28. So RD is equal to 3.5. If I put the value of RD in equation number 1, I get RA is equal to 2.5. Reactions, that is RA is equal to 2.5 kilonewton and RD is equal to 3.5. Let us move for the shear force diagram. To draw the shear force diagram, note down reactions RA and RD. After that, mark left and right hand side of each point load so that we are going to determine the value of shear force before point load and after point. Just extend the line to the point loads. This line represents zero shear force. As we are moving from left of A to right of A, there is an addition of force 2.5 kilonewton and which is upward in nature, so it is positive. After that, from right of A to left of B, no load condition is there. Whenever no load condition is there, we are getting a constant shear force. So here is the constant shear force. After that, we are moving from left of B to right of B. There is a decrease in load. So 2.5 minus 2 is 0.5. So there is a decrease in shear force here. After this, from right of B to left of C, no load condition, we are getting constant shear force here. That is 0.5. Moving from left of C to right of C, the decrease in load, that is minus 4 kilonewton. 0.5 minus 4 is minus 3. So here we get decrease in shear force. After this, right of C to left of D, there is no load condition, so we get the value of shear force 3.5 constant shear force. If I move from left of D to right of D, value is minus 3.5 and this is addition of force, that is plus 3.5. So minus 3.5 plus 3.5 is 0. So we can see we have drawn a shear force diagram which represents the value of force at individual point. SFD, which is in kilonewton. So above part of this line represents positive shear force. Below part of this line represents negative shear force. Shear force is in kilonewton. As we have drawn the shear force diagram, it is necessary to write down the shear force calculation. So shear force at A is 2.5 kilonewton. At LHS of B 2.5 kilonewton, RHS of B 0.5 kilonewton, LHS of C 0.5 kilonewton, RHS of C minus 3.5, LHS of D minus 3.5 kilonewton, RHS of D, that is 0. So this is how I have explained how to write shear force calculation. After this, we are moving for bending moment diagram. This line represents zero bending moment. So for bending moment calculation, clockwise moment as negative and anti-clockwise moment as positive. So bending moment at A and D are 0 because At point A and D, supports are there. So this support resists the bending moment. So bending moment at support always zero. Bending moment at point B. Here we are going from left to right. So we are considering the right hand part of this. So we are not considering the left hand part. So moment we are taking at point B. So moment of 2 kilonewton becomes 0. Next 4 into 4. Next 3.5 into 6. So 4 into 4 is clockwise in nature. So minus 4 into 4. Next 3.5 into 6. 3.5 is anti-clockwise in nature. 3.5 into 6 is negative. So if I do this addition, 5 kilonewton. So we can represent the value of bending moment at point B in the diagram. That is 5 kilonewton and line joining from 0 to 5. After that, bending moment at C. We are considering the right hand part of C. 4 kilonewton load is applied on part C. So the moment of 4 kilonewton becomes 0. Next is 3.5, which is 2 meter away from here, which is anti-clockwise in nature. So plus 3.5 into 2 is the moment of this 3.5 kilonewton force, that is 7 kilonewton. So this is the bending moment at point C. So we are plotting over here. 7 is slightly above the 5. So we can represent over here. We are joining this 5 with 7 by line. After this, we can join this 0. So this is my bending moment diagram. Positive BMD. Unit of BMD is kilonewton meter. So this is how we can move for SFD and BMD with the help of simple steps. Let us see another problem. Draw SFD and BMD for a beam as shown in figure. So this is the beam carries 2 kilonewton per meter as a UDL over a 2 meter span. 1 kilonewton point load at 3 meter from point A. Anti-clockwise moment of 4 kilonewton meter, which is 4 meter away from point A, and a uniformly varying load of 3 kilonewton meter, which is 2 meter away from point B. Let us move for the calculation. Summation of Fy is equal to 0. At point A and B, supports are there, so these are offering the reactions. So Ra and Rb are vertically upward, and the rest of the things are vertically downward. So Ra plus Rb minus this 2.2 kilonewton meter is a UDL. Convert this UDL into point load. So 2 into 2 is the conversion of UDL into point load, which is downward in direction. Minus 2 into 2. Next, minus 1 is the value of point load over here. We are doing here summation of forces. So 4 kilonewton is a moment. So we are not considering the moment over here. Next, conversion of this UVL into point load. That is, this is a triangle. So we are going to convert this UVL into point load such that area of this cross section is nothing but a conversion of UVL into point load. So 1 by 2 into base is nothing but 2 meter, height that is nothing but 3 kilonewton. So 1 by 2 into 2 into 3 is nothing but conversion of this UVL into point load is equal to 0. Next, we are getting Ra plus Rb is equal to 8. Summation of moment about point A is equal to 0. So moment of this Ra becomes 0. Afterwards, we are going for moment of 2 kilonewton per meter, 1 kilonewton, 4 kilonewton meter, and 3 kilonewton. So convert this UDL into point load. 2 into 2. After conversion of UDL into point load, it will appear as center position, means this distance is 1 meter. So minus 2 into 2 into 1 is a moment of 2 kilonewton per meter. Next, 1 kilonewton is 3 meter away from point A. So minus 1 into 3. After that, 4 kilonewton meter itself a moment which is anti-clockwise in nature. So plus 4. After that, 3 is the value which I am getting from here. That is 1 by 2 into 2 into 3 is the conversion of UVL into point load. We are converting the value of UVL into point load. It will appear at this position. So this distance is base by 3. So base is 2 divided by 3 and this distance is 2 base by 3. So 2 by 3 plus 5 is the distance of point load from point A. We get this value. After that, Rb, which is 7 meter away from point A. So plus Rb into 7, which is anti-clockwise in nature, is equal to 0. So we get Rb into 7 is 20. If I do the calculation, Rb is equal to 2.86 kilonewton. If we put the value of Rb in equation number 1, I get Ra is equal to 5.14. So it is important here to know how we are converting the value of UDL into point load and how we are converting the value of UVL into point load and how we take the distances. This is important. So to draw SFD and BMD, mark the value of RA and RB in the diagram. Just extend the point from the this is the line which represents 0, 0 shear force. If I move from left of A to right of A, there is an increase in shear force. So it represents here 5.14, which is rising in nature. If I move from right of A to C, there is no point load over here, so I'm not considering left and right hand part. I'm just considering a single part. So at point C, there is a UDL. I want point load over here. So 2 into 2 is the conversion of UDL into point load here. So 5.4 is the value at this point, minus 2 into 2, that is 4. 5.4 minus 4 is the value, that is 1.4. I get. I'm joining this by means of an inclined line. After this, I move from point C to left of A. There is no load condition, so I get a constant shear force over here, that is 1.4. After that, I am moving from left of D to right of D. There's a decrease in shear force, 1.4. So 1.4 minus 1, that is 0.4. I am moving from this point to E point. There is application of couple over here, which is not a force. So I'm not considering any kind of load over here. The effect of couple is negligible in the shear force. If I move from point E to point F, there is no load condition. So I get again constant shear force, that is 0.1. Move from F to left of B, there is a UVL. So I need to convert this UVL into point load. So 0.14 minus 3 is 2.86. We get a parabolic nature of a shear force. After moving from left of B to right of B, there is an increase in shear force, that is 2.86. Here minus 2.86 plus 2.86, we get 0 shear force. So this is how I achieved SFD from different nodes. This part is represent positive shear force and this part represent negative shear force. Here, shear force diagram crosses the 0, 0 line. So we can call this as a 0 shear force line, which represents point of contraction. Let us move for the calculation. These are the shear force calculation which we will be obtaining from the diagram. Shear force at point A, 5.14, at point C, 1.4, then at point D, that is 1.4. RHS of D, 0.14. Point E, 0.14. At point F, 0.14. At left hand side of B, minus 2.86. And at RHS of B, that is 0. So this is how we have drawn shear force diagram. We are obtaining the calculation from diagram. And moving for BMD, clockwise moment negative, anti-clockwise moment positive. Bending moment at point A and B is 0 because support resists the bending moment. Bending moment at point C. So we are considering the right hand part of C, 1 into 1, clockwise in nature. Then this is itself a moment, 4 kilonewton, which is anti-clockwise, positive. After that, we have converted this UL into point load 1 by 2 into 2 into 3. So 2 get cancelled down, we get a 3 kilonewton load over here, which is 2 by 3 distance from point F. So 3 is the value of point load into 2 by 3 is this much distance. We want distance from point C. So 2 by 3 plus 3 is the distance from point C to this point load. So 3 into 2 by 3 plus 3 is the moment of this UVL. After that, 2.86 is 5 meter away from here, which is anti-clockwise in nature. So plus 2.6 into 5. So we get this calculation 6.3 kilonewton meter. We have represented with the help of a parabolic curve as UDL is here. Bending moment at D, 4 is anti-clockwise in nature, so plus 4. Then 2 plus 2.3 into 3 is the moment of 3 kilonewton UVL. After that, 2.6 into 4 is the moment of 2.86, which is anti-clockwise in nature. So this answer is 7.44 kilonewton meter. We have represented in the diagram by inclined line. Now, as press C, this whenever we are going for shear force calculation, we are considering the left hand and right hand part of the load because it shows the abrupt change in the SFD. Similarly, for this is a moment, so we have to take the left hand and right hand part, right hand section to this to see the abrupt change in the moment. So we are considering the left hand part of moment. So we are considering the effect of this couple. So bending moment at left hand at E is, we are considering this anti-clockwise, which is plus 4. Then 3 into 2 by 3 plus 1 is the moment of this UVL. Next, plus 2.86 into 3 is the distance from point E. So this 3 moment of 3 is anti-clockwise, which is minus this moment of 2.86 plus and itself a moment 4, which is a positive. So this is how we achieved the moment at LHS of E 7.58, which represents the diagram. Bending moment at RHS of C. So here just we are neglecting the effect of couple, rest of the things are same. So we are removing this value, that is 4 kilonewton meter. So we have moment of 3 kilonewton UVL and moment of 2.86 kilonewton point load, that we are getting 3.58. So here we get bending moments, as we are considering the left hand part considering the effect of couple, and right hand part neglecting the effect of couple. So we are getting sudden decrease in bending moment here due to the anti-clockwise couple. Now we are moving from point E to point F, bending moment at point F. So we have a UVL over here. So 3 is the point load and this much distance is 2 by 3. So moment of UVL is 3 into 2 by 3, anti-clockwise in nature. Then 2.86 into 2 is the clockwise moment. So we get moment at F is 3.73 over here, which is represented in the diagram. So this is how we have achieved the SFD and BMD up to this point. It is necessary to calculate the value of bending moment at this point, because where we are getting the shear force 0 means somewhat bending moment at this position, which is pure bending moment. So we have to calculate this pure bending moment. So we need to find the distance from point B. Let us move. So to do this, we are considering this, we are just extending this line towards at this point. We are marking this point as a point G. Assume distance from B to G is X meter and point load as a W kilonewton. And we have a reaction of 2.86 kilonewton, point B. So we are using here summation of shear force at point G is equal to 0. So vertically upward force positive, downward force negative. So convert this UVL into point load. 1 by 2 into base is X and height is W. So 1 by 2 into W into X, the shear point load which is applied over here, which is downward in nature. So minus 1 by 2 into W into X. Next, plus 2.86 is vertically up. So we get here W into X is equal to 5.72, which is equation number 1. Next, I'm just taking this triangle of 2 meter base and 3 meter height over here. So I use a similarity of triangle method to determine the value of W in terms of X. So 3 by 2 is equal to W by X. You can write that is equation number 2. So if I compare equation number 1 and equation number 2, I get the value of X is equal to 1.95, that is from point P, and W is equal to 2.92. So this is what the needed calculation for determination of bending moment at point G. So this is the distance X. This is the load 2.92 kilonewton. So bending moment at point G, W value is known to us. So convert this UDL into point load. 1 by 2 into 2.92 is the load into 1.95 is the distance. So we can say 1 by 2 into base into height. W is 2.92, X is 1.95. So this is conversion of UDL into point load into this distance is X divided by 3. X is equal to 1.95 divided by 3. This is the moment of uniformly varying load. After that, 2.86, which is X meter away from point G. So 2.86 into 1.95, which is anti-clockwise in nature. So we get bending moment at point G 3.72 kilonewton, which is positive in nature. So we are representing over here. So here is a bending moment where shear force is equal to 0, 3.72 kilonewton. So this is how we have calculated the shear force and bending moment. We are representing the values in terms of diagram. Thank you.